Hi guys, today's question is unquestionably the most infamous of them all. It's called the two sum needs no introduction. Now I'll say one thing, even though this is known by all as the most famous question, the solution I don't think is quite obvious. Once you know it, probably it is, but the first time to come up with it is quite challenging. There's a trick here, so let's go forward. You can read the question here, pause it, but basically I'll just explain what the question is. We've got an array of numbers, and then we've got a target here. So the question is can we find two numbers in this array that sum to the solution 9? And 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 that's the question. So there are a sequence of steps that one can think about to get the solution. The first is we can take the number 2 and then we can add the number 7 to it, and here we got a little lucky. We just got 2 plus 7 is equal to 9, but let's say the 7 was somewhere here, or there was a different arrangement of these elements. So in this case we'll have to keep on going forward. One thing for those who probably have not had a CS background, we are interested in the O of n complexity, which is the worst case complexity. So we have to look at what would have happened if this 2 was in fact here and 7 was in fact here. And in that particular instance, we would have had to do a number of iterations before we stumbled upon the right match. So we'll have to basically go through n minus 1 times for the first item, 2 plus 7, and then 2 plus 11, and then 2 plus 15, so on and so forth. Then we go on to the second element, then we'll have to do n minus 2 iterations. So basically, we are doing a sequence of n iterations for each number. So n iterations n times is an n square solution. So we kind of get an idea. If we were to do a run of the mill solution, we'll do an O(n) square complexity and we'll find it. So it's a loop within a loop. But the obvious question is, can we do better? And we'll think about it. What one can do is we can, so this is a second solution in the scheme of things that we're talking about. What we could do is we could sort this input, and sorting can be accomplished in O of in n log n time, and there are several algorithms that can help us do that. And what that could do, we'll see whether that is any helpful. But if we were to do that, then we can sort it in ascending order. So we go from 2 to 7 to 11 to 15. This is already sorted. That's another coincidence. But if we did that and then we ran a two pointer solution in O of n times. So let's say we started in the beginning with the smallest element here and with the highest element on the right side, and we said, what is 2 plus 15? That's 17. That's clearly greater than 9. So what do? We do we increase it or do we decrease it? And of course, we'll have to decrease it because we are already above 9. So what we'll do is we'll reduce 15 to 11 and we'll say 2 plus 11. What's the number? That's 13. Is that higher or lower than 9? Again, 13 is higher than 9, so again we'll reduce it further. So then we'll get to 2 plus 7. So what you can see is that once the array is sorted, we can go through the list in O of n fashion, but n is not the bottleneck here because we already spent n log n complexity just sorting it. So that is the bottleneck, and that means that we can solve it in n log n time, finding whether there are two elements that actually in fact add up to the target. Now this solution, the one that is actually supposed to be used here, that will yield a complexity of O of n, which is much better than n log n, and definitely no question against n square. And the answer to that is what if we have a hash map. So let's say we've got a hash map, and this is why I said this is not a clear, is not an easy solution before you know it. Once you do, maybe then it is. But the solution has a trick, which is that we will have a hash map and we will map the the number to the index, because here it says, given an array integer nums and an integer target, return the indices of the two numbers such that they add up to the target. So we have to in fact return the indices and not the numbers themselves. So what we'll do is we'll have a hash map and we'll map the number to the index, and then we look at the difference between the target and the number we are looking at and see whether that difference is already present in the hash map. So let's say we start with a 2. So the hash map is initially empty. We start with a 2 and we say is the number 9 minus 2, which is 7, already in the hash map? And of course it's not, because the hash map is empty at this point. It's not there. So what we'll say is, okay, it's not there, so let's add 2 with the index 0 to the hash map. Then we go on to 7. And then what will we say? We'll say, is the difference of 9 minus 7, which is 2, present in the hash map? And why are we doing that? We are doing that because once we find the difference, then we know that this thing and this thing will add to this. So of course, in this case, we find, yes, this is already in the hash map. So we'll return a true, and we can return the index of this and this. But if that was not the case, we would have gone on and on until we went through the entire list. If we found something, we would have returned true, otherwise would have returned false. So enough of the explanation. I think we covered all the scenarios. Now I think it's time to code. So first thing is, we just have to uh, initialize a hash map. And I have a habit of doing Control Enter because I'm used to doing coding in VS Code. So forgive me doing Control Enter here. But now we'll go through the list, and let me write it first. So what is enumerate? Enumerate basically helps us go not only through the items, but through the elements of the array, but also through the indices in the same time. So I would be the index, so it's basically 0, 1, 2, 3, and n would be the element 2, 7, 11, 15. So all the both of them we can get it simultaneously, and that would be beneficial to us because we have to map the element or the integer itself, and the value should be the key. So before we do that, we can say what is the difference, because that's what we were seeing, whether this is already present in the hash map or not. So the difference would be target minus n. So that's what we have. And we'll say, is if the difference is in the hash map, then what do? Then we return um, the index where this difference is the index of the difference. So that would be hash map difference, and then the index that we have currently for this element that we were looking at, which is I. But if that was not the case, meaning if the difference is not there, then we'll say hash map of n is equal to I. So if the difference was not there, we have to add it. And if we go through the entire list and we never find a difference between the element that we are looking at and the elements and the target element, and the difference is not already in the hash map, that means there are no two integers that would sum to the target. So in that case, we'll have to return a false. And that should be it. Okay, it's giving a runtime error because I said, okay, I misspelled it. Enumerate. So it seems to pass these solutions test cases, and it passed fine. Not sure why it's saying beats 35% in memory, but this seems a little random. We did have to use, so here's the thing. If we use a hash map, we are using O of n extra memory. If we went through the two loop solution, which we spoke about, the O(n) square solution, or in fact even the sorting solution, we would not have had to use extra memory. But in that case, our runtime complexity would have suffered. So always in complexity problems, or I probably should not say always, but many a times it's a contrast, because you can improve runtime, but then the memory would be affected, and sometimes the runtime would be worse off if the memory is if more memory is being used. So there's a tango there, but here we have to find the best runtime solution, which is O of n, even though it consumes O of n memory. So I think that's enough, but we'll see you in the next one.